Hello, and welcome to this Thermo Fisher Scientific webinar entitled Better Rheological Results, How to Select the Right Geometry for Tests with the Rotational Rheometer. My name is Fabian Meyer. I'm Senior Application Specialist for Rheology at Thermo Fisher Scientific, and I will be the host of this webinar. Before we go into the details, let me run you briefly through the content of this webinar. I will start with giving an overview of the standard geometries available for conducting measurements with rotational rheometers. Then I will talk about some general considerations on how to select the right measuring system before discussing the details about how the rheometer performance, the viscosity of the sample, the size of the dispersed particles, and potential sample slippage influence the choice of the measuring geometry. After talking about the details of the different measuring systems, I will close this webinar with a general overview of different types of samples and the most suitable measuring geometries for testing them. Selecting the right measuring system is highly important for obtaining reliable and reproducible results when performing rheological tests. There are many different types of geometries available, and also different dimensions, shapes, and even surface finishes. The ideal choice does not only depend on the sample properties, but also on the type of test to be performed, the rheological parameters to be measured, as well as the measuring range of the rheometer itself. This webinar is intended to provide an overview of the available options and give some first guidance on how to select the optimal geometry for a specific measurement task. On this slide, you see an overview of the most common measuring geometries. On the upper left side, we have cone and plate and parallel plate geometries. Next to it, the different types of coaxial cylinder systems, according to DIN/ISO standard, with the recess at the bottom of the rotor, double gap, and Mooney-Ewert type coaxial cylinder geometries. On the lower half, we have Vane and spindle type geometries. Both types of geometries provide relative and not absolute data, and the latter one is mainly used with simpler rotational viscometers. The lower right of the slide shows geometries for specific type of measurements, including a fixture for performing rheological tests in extension, a setup for testing solid specimen, and a so-called bicone setup for running rheological tests at the interface between two liquid layers. Which geometry is the right for a specific rheological test depends on three things. First, the rheometer itself. What is the torque and rotational speed range of the instrument? Does it have a highly sensitive air bearing or a less sensitive mechanical bearing? And is the instrument equipped with an automatic lift, or does it require manual gap setting? The second factor is the properties of the sample to be tested. What is the viscosity and the consistency? Are there any particles dispersed? And if that's the case, what is the maximum particle size? The last factor is the test that is intended to be performed. Are you looking for absolute or relative data? Are you changing the temperature during the test? Do you want to perform tests in oscillation or in rotation mode? And do you want to apply axial forces during the measurement or even measure the first normal stress difference? So let's start with the rheometer performance. On the right side of the screen, you see a plot that shows the theoretical measuring range for different rheometer geometry combinations, and viscosity and shear rate. The larger the parallelogram, the wider the measuring range of the combination. In general, we can say that the smaller the torque range of the rheometer, the more attention has to be paid when selecting the measuring geometry. The green parallelogram represents the measuring range of a rheometer equipped with an air bearing and a 35 mm 1 degree cone and plate geometry. The measuring range is so big that most liquid and semi-solid samples can be tested with this setup. The blue parallelograms represent the measuring ranges of a rheometer with the mechanical bearing and different types of geometries. The ranges for the individual geometries are significantly smaller compared to the air-bearing rheometer, and the utilization of different geometries is required when sample properties change from low to high viscous. The measuring ranges can be obtained from the range calculator, which is a sub-program of the Vane Rheometer control software. This tool can display the theoretical measuring range from any available measuring geometry rheometer combination. Besides the total measuring range in shear rate, shear stress and viscosity, the range calculator can also calculate the test range for a specific reference sample. This slide gives some first guidance for identifying the best measuring geometry depending on the sample properties. Low to medium viscous materials that flow easily and are also easy to clean can be measured with coaxial cylinder type geometries. More paste-like samples with a higher viscosity and a higher yield stress can be tested with cone and plate geometries if they don't contain any or only very small dispersed particles. If the particle size exceeds a certain limit, parallel plate systems should be used. For inhomogeneous samples that contain very large particles, using Vane-type rotors might be the best and sometimes the only option. However, since the flow field around a vane is not uniform, these type of setups only deliver relative and not absolute viscosity data. When it comes to the viscosity of a sample, rule of thumb says that the higher the viscosity, the smaller the surface area of the measuring geometry should be. Double gap geometry, with their large surface area, are ideal for testing low viscous samples such as water, diluted polymer solutions, or low viscous oils. The other extreme is highly viscous polymer melts or concentrated polymer solutions. For these types of materials, a parallel plate or cone and plate geometry with a small diameter is ideal. The plot on the right shows again the theoretical measuring range of a large double gap and a small 20 mm parallel plate geometry. The green line represents the viscosity of water at 1 millipascal second. It can be seen that the sample or a sample with such a low viscosity can be tested over a much wider range with the double gap geometry. When a material is tested that contains particles, special attention has to be paid to the measuring geometry or the measuring gap. According to international standards, the measuring gap should be 10 times bigger than the maximum particle size. Cone rotors have a small truncation gap, which depends on the cone angle and ranges usually between 20 and 150 micrometers. That's why cone and plate geometries can only be used if the sample contains no or only very small particles. For sample with particles up to a few hundred micrometers, parallel plates and coaxial cylinders according to DIN/ISO standard or with the recess at the bottom of the rotor can be used. When a sample contains particles in the range of 500 micrometer or larger, relative measuring geometries like Vane rotors have to be used. Some materials might show slippage during a rheological test. In that case, the tested material is not sheared or deformed homogeneously anymore, and the obtained results are not correct. In order to avoid or at least minimize the effect of slippage, geometries with a profiled instead of a smooth surface can be used. Different types of profiles are available for parallel plates and coaxial cylinders. Now, let's have a closer look at the different measuring geometries and start with cone and plate geometries. Cone and plate systems consist of a cone-shaped upper rotor and a lower flat plate and are available in different diameters and with different cone angles. A big advantage of the cone and plate geometry over the parallel plates is that the shear rate is constant over the entire radius. They are suitable for testing low to high viscous liquids as well as weak semi-solid materials such as emulsions and dispersions that contain only small particles. Cone and plate geometries also deliver correct results for the first normal stress difference in rotational tests. The first normal stress difference is a measure for the elasticity of a material. Parallel plates consist of a flat plate rotor on a lower flat plate and are available in different diameters. An advantage of this system is that the measuring gap is not fixed like for cone and plates, but can be adjusted according to the sample properties. A disadvantage of parallel plates is that the shear rate is not constant over the radius of the measuring gap. The maximum shear rate is applied at the rim of the rotor, while in the center the sample is not sheared at all. This is why the parallel plates deliver accurate results only for Newtonian samples in rotation and in oscillation when the tests are performed within the linear viscoelastic range of the sample. The difference of the measuring results for a non-Newtonian standard materials are shown here. At low shear rates, where the sample still behaves Newtonian, both systems deliver the same results. However, once a critical shear rate is reached and the viscosity starts to decrease, only the cone plate provides absolute data. The more shear thinning the material, the bigger the difference between cone and plate and parallel plates. This slide gives an overview of the standard coaxial cylinder geometries. They all consist of a rotating bob and a static bottom cup. Such a combination is also referred to as a Searle geometry. In general, coaxial cylinder geometries are suitable for pourable, low to medium viscous liquids. They should not be used for materials that exhibit a high yield stress. At high shear rates, the flow in a Searle-type coaxial cylinder system will become turbulent. The onset of turbulent flow also depends on the sample viscosity and the density. Let's have a closer look at a coaxial cylinder geometry with the recessed end. When the rotor is immersed into the cup that holds the sample, an air bubble is trapped in the lower recess. This bubble minimizes the torque contribution from the lower bulk liquid. The upper reservoir can collect small amounts of sample overfilling. This type of geometries can deliver highly accurate results, but it might be necessary that overfilled sample that creeps up the cup wall instead of flowing into the upper reservoir is removed first. Otherwise, this material will contribute to the total torque and the obtained results are not correct anymore. These geometries are not suitable for temperature ramp or step experiments due to the expansion or shrinkage of the air bubble at the bottom. The coaxial cylinder geometries according to DIN 53019 or ISO 3219 consist of a static cup and a rotor with a conical tip at the bottom. These coaxial cylinders are available in different sizes, but the dimension ratios of the cup and the bob are completely standardized. Some of the relations are shown here on the lower right. Unlike the coaxial cylinder geometries with the recessed ends, these geometries can be used also for performing temperature ramp or step experiments. Double gap coaxial cylinder geometries have an inner and an outer ring gap with a large surface area. Since the radii ratios for both gaps are identical, the sample is exposed to the same flow field everywhere inside the geometry. Double gap geometries are suitable for very low viscous liquids, but not for samples that contain larger particles. Besides the cylindrical measuring gap that is common for coaxial cylinders, Mooney-Ewert type geometries have an additional conical gap at the bottom. They are designed in a way that the shear rate in both gaps is identical. Mooney-Ewert geometries require only small sample volume but still offer large shear surface and are therefore suitable for low viscous liquids without bigger particles. Due to the small truncation gap at the bottom, a precise axial gap setting with an automatic lift is required. Vane type geometries are usually used for measurements in the original sample container or in larger laboratory beakers. Since the flow field around the Vane rotor is not uniform, they only provide relative viscosity data. Vane rotors are used when the sample contains particles that are too big in size for any of the narrow gap measuring geometries, or when the microstructure of the sample will be irreversibly destroyed when forced into small measuring gaps. Since the shear stress at the outer rim of the vanes can be calculated, Vane rotors are suitable for measuring the yield stress of coarse dispersions and samples with fragile gel structure. Besides the discussed standard measuring geometries for rheological tests, there are various special geometries available for specific applications. Some of them are shown on this slide. When using the solids clamping tool, a rotational rheometer can be used to perform dynamic mechanical thermal analysis with solid specimen. This type of analysis is used, for instance, to determine characteristic phase transitions of a material, such as the glass transition. The St. Manon Extensional Rheometer tool extends the capabilities of a rotational rheometer towards extensional testing. A polymer film is clamped on two drums that then perform a counter-rotating motion. During the test, the polymer film is stretched and the resistance against extension can be measured. The illustration next to it represents a tribology measuring cell for rotational rheometers. Tribology is the study of friction, lubrication and wear, and with this setup such tests can be performed also with a rotational rheometer. The last example shows a so-called bicone setup which is used for interfacial rheology. A bicone rotor with sharp edges is placed either at the interface between two liquids or at the surface of a single liquid phase. It is used to measure the rheological properties of small interfacial layers that form between the bulk phases. These interfacial layers can, for instance, consist of surfactants that migrated from the bulk liquids. These are only 4 examples of measuring geometries for specific applications that make rheometers a more universal platform for material testing. You will find more examples on our websites or in our instrument brochures. When rheological tests are performed in oscillation mode, some other factors have to be considered when selecting the right measuring geometry. Measuring systems with heavy rotors should be avoided in order to minimize the negative effect of instrument inertia. These types of systems include coaxial cylinder geometries with a larger diameter and a heavy bob, and to a lower extent also parallel plates and cone and plate setups with larger diameters. Besides for tests in oscillation mode, instrument inertia can also affect the results of tests in rotation when the shear rate is ramped up or down very fast. Instrument inertia can be neglected for steady-state experiments in rotational mode. When performing oscillatory tests with low viscous materials, a geometry with a small measuring gap should be selected in order to minimize the influence of sample inertia on the test results. For such tests, either parallel plates and a small gap height or cone and plate geometries with a small cone angle can be used. This slide gives a general overview of different types of samples and shows the most suitable measuring geometries for testing them. We are covering consistencies from very low viscous all the way up to fully solid. In most cases, you have more than one option, and the ideal geometry also depends on the type of test you want to perform and the parameters you want to measure. And with this slide, I will end this webinar, but before I do that, I will just quickly summarize the things I have presented so far. So choosing the right measuring system is important for getting reliable and reproducible data for rheological tests. The most common rheological measuring systems include the different types of coaxial cylinders, parallel plates, cone and plate setups, as well as various types of vane rotor geometries. Which is the ideal system for a specific measurement task depends on several things. This includes the rheometer performance, or to be more precise, the measuring range for torque and rotational speed, the sample properties such as viscosity, particle size, and the tendency towards slippage, and the type of rheological test you want to perform and the parameters you want to measure. This can include temperature ramp experiments and measurements of the first normal stress difference. Besides the standard rheological measuring systems, there are a lot of special measuring setups that are used for performing specific rheological tests. This includes setups for dynamic mechanical thermal analysis, extensional testing, tribology, as well as interfacial rheology. And with this, the webinar is finished. Thank you very much for your attention, and goodbye.